Okay. Okay, so I think we can get started. Our current chapter is the chapter on single source shortest path. We have already seen the Bellman-Ford algorithm, where we go over all the edges v minus 1 times, and each time we do relaxation per edge, the relax operation, and the complexity of this algorithm is E times V, because we go over all the edges V or V minus 1 times, and the which is a downside, the complexity, because we would like it to be closer to linear meaning E plus V, size of the input. The advantage is that this algorithm works even when the weights of the edges can be negative. We already discussed the topological sort case, meaning where the input is directed acyclic graph. And I made the quick comment that basically the algorithm of starting with vertices in degree 0, removes them, mark the shortest path to all vertices you can reach from them, and then keep removing vertices within degree 0, which is basically the same algorithm that we studied for topological sort, gives us the single source, or all source, if you will, shortest path, longest path, whatever you want. Let me make a point that the longest path here may be relevant if this models an engineering project. And for that reason, this may be relevant. Would like to know the longest path, for example. It may tell you the shortest time by which you can complete a complex project. Because if there is some critical path that holds you back, it is that's going to be the problem. And this type of modeling, by the way, is often used in dependence graphs in compilers. And so this is a pretty useful model tool, the directed acyclic graphs and the various computations that we are talking about. So in optimizing compiler, it plays a very big role. However, since we already discussed directed acyclic graphs in the section on depth first search, where we discussed the alternative direct algorithm for directed acyclic graphs, I'm not going to elaborate on it here. Okay, Dijkstra's algorithm. So Dijkstra was a well-known Dutch computer scientist. And as you can see from these algorithms, it was pretty easy to have an eponym algorithm in the early days of computing, simply because the simplest problems were up for grabs. Still, it's a nice algorithm, and it belongs in standard textbooks and is being taught everywhere. So what is the basic conditions or assumptions underlying this algorithm? So unlike the Bellman-Ford algorithm, here edge weights cannot be negative. So what if you have a negative edge weight? Then you don't apply this algorithm. It stops being correct. Okay, so it's a It's a clear-cut assumption that is being made upon actually even considering Dijkstra's algorithm. So we are going to use the same notation as before, d of s, to relate to the computed distance or d of v, the computed distance of a node v from a starting node s. So remember, it's a single source, shortest path. So we have a node S, which comes together with the input. So the input includes the graph GVE, V is the vertices, E the edges, and the edges have weights. The weights are non-negative, and the input also includes a node S, which will be the source node. So one thing we can say upfront, and that's what we do in step 1 of the algorithm, we can declare the distance to the source node S to be final, simply because it is 0. You know, you are there already, so there is nowhere to go. So that's a trivial point. Okay. So, so we can finalize that, and the whole idea of the algorithm will be to finalize the distance to one node at a time, because the claim is going to be that we are in a position to finalize the computed distance to a node, and we are going to claim later in the correctness claim that if we do it one node at a time in a certain way that I'm going to explain, which is the heart of Dijkstra's algorithm, then the computed distance will be the correct distance. So now that you know that we are going to finalize the distance to one vertex at a time, let's see how step 1 goes. So in step 1, we just finalized the distance to the source node. We declared it as 0. Now we go over all the edges that depart node S to any vertex, and now we go and relax it. So where you can, for example, see that is right here under step A. Initially, the situation is that this is the graph, and the distance to every vertex is infinity. Why infinity? Because we don't know how to get there. We initialize the distance to S to be 0. And what will happen in step 1 after doing the relaxation? So you can see here that we are talking about a directed graph, and these are the weights, what you see on the edges. What we do, we relax all edges S to U for every vertex U. So let's see which vertices U have an edge from S. In this example, it's vertex T and vertex Y, right? Vertex X and Z do not have a direct edge leading from S. So what we do, we go to this over all the edges that depart, that exit S, and we try to relax. So clearly, if we can reach any vertex here, assuming that we have a finite weight or length to the edges, we are always going to beat infinity. So this guy, so through S, you have d of S plus 10, which is clearly better than infinity. So it's 10, and we buy that. Here we say distance S plus 5, it's better than infinity for Y, so we write 5 here. Okay. So this is the very first iteration of the algorithm. Now, you already got the spirit of the general iteration, but what you have not yet seen is the which vertex we are going to finalize the distance to next. And here is the whole idea as written in step 2, which is the general step of the algorithm. So we have the vertices that we finalized. So far, we finalized only the distance to S. So now we are going to look at all the vertices whose distance was not finalized, meaning in this case, all the vertices, and we pick the one for whom it's a mistake, it's D of V. It should be D of V. Or no, D of U. Oh, let's see. Oh yeah, the vertex whose D, let me put it this way, better to put it D dot, is minimum over this following set. So we look at over all the vertices U for whom the distance has not yet been finalized. And we pick the one for whom the distance is minimum among all the vertices that to whom the distance has not been finalized. The one that gives me the minimum, we finalize its distance. So we add it, we move it to the group of vertices whose distance was finalized, because we are going to argue that this is the real minimum. And now we are going to consider shortest path going through this vertex that we just finalized. So what are we going to do? We are going to review all the edges that depart from V and go to any other vertex and use these edges to relax the D value on the U side. So let's see how we are going to do it. After this round, we look at the 4 vertices which have not yet been finalized, T, X, Y, and Z. Which one has the minimum D? Clearly 5. Clearly Y, which has 5, right? Because we have 5, 10, infinity, infinity. 5 is the smallest. So we finalize the distance to Y, okay? And then, after we do that, we look at all the outgoing edges from Y, and we relax them. What does it mean? It means that going in the direction of T, we have 5 plus 3, and we ask, is it a better deal than 10? Answer, yes. So 5 plus 3 is 8, so we replace the 10 by 8. Here we go and we do 5 plus 7, and we offer a I'm confused. Oh no, okay, I'm sorry. Just a second. What's going on here? Oh no, it's 9. Okay, I'm sorry. Yeah, this value is 9. You see, this confused me. Okay, I'm sorry. Okay, so 5 plus 9, I didn't understand how they reach 14. I thought that I read 7 here for some reason. My mistake, I'm sorry. So 5 plus 9 is 14. 14 is better than infinity, so we change the label of X to 14. Here, we offer Z 5 plus 2, which is 7. 7 is better than infinity, we change it to 7. Okay, next round. In the next round, we have 2 vertices whose distance was finalized before, S and Y. Whom is to be finalized next? So we have 3 vertices that have not yet been finalized. Which one has the minimum? D. The answer is Z, which has 7. We have 7, 8, 14. 7 is the smallest. We finalize the 7, and now we move 7 to the group of vertices to whom the distance has been finalized. And now we try to relax over all the edges that exit 7. So there is an edge leading to X, and this edge now will be 7 plus 6. So it offers 13. 13 is a better deal than 14, so we change the value to 13. The next thing that we do is we have now 3 vertices, all the black ones, to whom the distance was finalized. We have 2 who were not. We look at the 2 who are not, and we ask which one has the lowest label. 8 is smaller than 13, so we finalize the distance to t. And now we relax on the outgoing edges of t, only the ones that lead to vertices that have not yet been finalized. We don't bother with edges that lead to vertices that have been finalized. So now, after doing that, we look right here, and we do 8 plus 1, and this makes it 9. 9 is better than 13. And finally, we finalize 9, and that's the end of the computation. Okay, so is the flow of the algorithm clear? We keep adding vertices. Each time we add a vertex whose distance is the smallest among the not yet finalized vertices. This is the whole Dijkstra algorithm. Other questions about this algorithm? I'm going next to reason about its correctness.
Yes, Professor.
Please.
Yeah, so when we were at node Z, whose value was 7, so how did we came back from 7 to again 5? Like, I mean, is it continuously expanding every node, or
No, we didn't go back to 5.
so when we were at 7 and we saw that, okay, 6 is the minimum, I mean, the
So which stage are you in? A,
D,
B, C, D, E, or F?
D for doll.
D, okay. So at D, uh, what the current situation is the following. We already finalized S, Y, and Z, right? They are black. Okay. So
Okay.
what's going on at this stage is we choose the 8, we finalize it, and we update the distance to X. So we finalize T, and that's what's going on here in step D.
Okay, okay. So first we
So maybe you
finalize.
wanted to ask about step C. I don't know, up to you, but just guide me where you are.
First, the X node was 14, then it was updated to 13.
Just a second. What step are you in? Just
From
A,
C to
B.
D,
I'm sorry?
from step C to step D.
Okay. So let's do one step at a time.
Hmm.
Okay, so I'm in step C.
Okay.
In step C, I just declared Z to be finalized, right?
Yeah.
Okay. And now, which means that its distance is 7, okay? But now, so this is what is reflected here. And now what is going on, before we move to selecting the next vertex, we relax based on all the outgoing edges, going from the node we just finalized to any other node. In this case, and to any other node which has not yet been finalized. So we don't go to S. But here we have outgoing edges to S and to X, right?
Yeah.
So the only edge which invites a relaxation is the one going to X. So we do 7 plus 6, which gives me 13, which is better than 14. So I update it to 13. And
Yeah.
now I move to the next stage, to the next iteration, where I now select the vertex with the smallest label, which is T, because T has 8 and this has 13.
Okay. Okay.
So
Yeah.
is it coherent now?
Yeah. Yeah.
Okay. So what you really need to understand, you need to put a full stop after each of these instances, because it's more of a snapshot. You don't have a movie, right? So there's no animation here. So it's more a frozen picture where we do some jumps and we tell you some things that some of them happen, if you will, serially, but it's I hope by now it's clear in what way the stages reflected in this figure depict the iteration. Okay. Okay, so I hope that this was clear. Other questions about the algorithm in this drilling example, at least, or in general? So I do owe you now, of course, the correctness. Yeah. Anybody wants to ask a question? Okay, so if not, I'm going now to move to the next slide, which will offer the correctness. So we have here really two quantities. Quantity one is d of v, which is the distance that we compute. And it becomes most relevant when we finalize it. So d of v is the computed entity. Delta S of v is the correct value. That's the ground truth, okay? Delta S of v is the correct distance, is the shortest distance from S to v. D of v is the computed distance. And of course, for correctness, what are we going to argue? That following iteration I, d of v is equal to what it should be equal to, meaning the correct distance from S to v for every vertex v whose d of v was finalized by the end of iteration I. Okay, so what we are going to say, and that's an inductive claim, is that everything we finalized up to the end of iteration I was correct. And by now, I hope that you see why when we have such an inductive claim, automatically you should understand for yourself what is the inductive hypothesis, right? The inductive hypothesis is that following iteration I minus 1, d of v was equal to delta S of v for every vertex whose d of v was finalized by the end of iteration I minus 1. Okay, so by now, I don't need to state for you both the hypothesis and the claim. It's enough to state one. You're already trained enough to derive the other, right? Okay, so now let's see how the inductive proof works. We assume the inductive claim or inductive hypothesis for I minus 1, which I just spelled out for you, and suppose that d of u is finalized in iteration I. So observe that because we finalized one vertex in every iteration, what I will finalize by the end of iteration I will include everything that I finalized before. But for all the vertices that were D was finalized before, the application of the inductive hypothesis is trivial, right? Because I assume that everything that was done by the end of I minus 1 was finalized, was correct. So the only vertex for which I need to prove anything is for the vertex that was finalized in the current iteration. Okay. So now there are really two cases. One case is that the shortest path to this vertex goes only exclusively through prior finalized vertices. Okay, so if it goes only through such vertices, the inductive hypothesis means that to every such vertex, the distance is correct. In particular, to the vertex leads me to you. Now, upon finalizing the vertex W that leads me to you, the algorithm relaxes all the distances, accounting for the correct distance to W and adding the edge WU, which means that if this is the case, the algorithm did it correct. Okay, so this is the easy case. The more intricate case is where there is a path of this form, where the shortest path from S to U goes through some vertices, so the set capital S as opposed to small s. Capital S is the set of all the vertices that have been finalized by the end of iteration I minus 1. So suppose that the shortest path from S to U, in case 1, it may go around here, but then it jumps to U. In case 2, it is much more complex. It may go through another vertex, may come back, goes out, may come back, and finally it ends up at U, meaning what makes case 2 different than case 1 is that the shortest path includes at least one vertex prior to U to whom the distance has not been finalized. Okay, so you can easily see that case 2 is the complement of case 1. And together they cover all the possibilities. Okay. So now, let's see what's going on here. We have a path P1 leading to this X. So if you look at the shortest path, you ramble, you go around S, and then there is a first time where you go out. And the first time that you go out, in case 2, you must actually hit a node other than U, because if it were U, we are in case 1. So let's call this node Y. What will be the key claim? The key claim is that you tell me that in iteration U, in iteration I, the element you chose to finalize the distance to is U. And I claim that by virtue of telling me that the shortest path goes through a Y, then may come back or whatever, and then reach U, this implies the distance to Y is less than the distance to U, in contradiction to your selection of U to be the vertex outside of S, which has the minimum D. So observe that here I relied strongly on the non-negativity of the weights of the edges. So that's really the end of the proof. So for that reason, by adding incrementally the next vertex to whom the distance is the smallest, I'm not making a mistake, and I compute incrementally all the correct shortest path to every vertex. So that's the correctness argument. Any questions about the correctness argument? If you want me to repeat it, please ask. Okay, if not, I will proceed now to the complexity argument. In the complexity argument, the reason that it is so short is because I'm going to reduce everything here to data structures that we have seen before. So basically, what do we really need? So we take originally all the vertices. Initially, their distances are infinity, right? All the vertices with the exception of S. And ask ourselves what happens to their distances for the sake of computing the minimum as we go. So whenever we pick a vertex, the first thing that we do, we relax all its outgoing edges. So to the extent that we find that we can decrease the d of a vertex, we go back to this data structure and do a decrease key query. Okay, so we have decrease key query. Per edge, we may do that across. So we have as many as order of E decrease key queries throughout the algorithm. It may be smaller, of course, in the case that the edges go backwards to vertices for whom the distance has already been finalized. But we are talking about a big O where we try to upper bound the number of queries. So the number of decrease key queries cannot exceed E. Okay. What is the other query we may want to apply? The other query we want to apply is finding the minimum. So what will happen is that when we find a vertex whose D is minimum, so first we need to figure out that that's the minimum, and then we need to remove it. So next time that we apply the minimum query, we never recompute the same guy that already we computed before. So how do we call this operation where we find the minimum and we remove the vertex? We call it extract min. So if you go back and look at your books or at the slides or at the textbook, you will see that we considered before data structures that support this family of queries, decrease key and extract min. And we can do that in E plus V times log V time. And we are not going to study, this can be improved to E, which is not a multiple of log V plus V log V. So the E, as I described it, is multiplied by log V, but it doesn't have to. But this is beyond scope for this class. So I'm done with chapter 24 in the book, in the text. Do you have any questions about it? Okay, so if you do not have questions about it, I'm going now to switch to section 25. Let me find it just a second. Okay. So section 25, which is really the last section in the so-called algorithm chapter, the biggest chapter in the current course, or let me call it maybe serial algorithms chapter, is about all pairs shortest path. So what is all pairs shortest path? In the single source shortest path, as you remember, we discussed the problem of finding the shortest path from a single vertex to everybody else. Here, we would like to find at once the shortest path from every vertex to any other vertex. So I hope that the problem definition is clear. And what I've done here, and if anybody would like it, please don't hesitate to send me a reminder after the lecture today. I went ahead and added 2 slides just because I felt that usually when I teach this class regularly, it's my first time, as you can imagine, teaching it on Zoom. I'm used to present the material in the next 2 slides on the board. But because of the Zoom delivery, I included extra slides to make it more understandable. So they are not included in the version of the slides that is now uploaded. They are pretty straightforward, but again, if anybody would like me to re-upload the set of slides, including the 2 I'm going to discuss next, just remind me, send me an email, and I'll be glad to do it. So I wanted to make a point here. So I hope that the problem is clear, right? The problem is all-pair shortest path. So I actually would like to argue that there is an algorithm for this problem, which I would argue that a good student who will get enough time to think about it could come up with it on his or on her or on their own, because it is really based on some limited manipulation of concepts that you have seen. Okay. So I'm going to try and explain why, in a way, you already know an all-pair shortest path algorithm, which is not too bad. And I'm going to do it by way of analogy. So the first thing I'm going to talk about here, imagine that I have a square matrix, A, whose size is n by n. Okay. So I guess you all learned, even in high school, how to multiply 2 matrices, and in particular, a square matrix by itself, right? You all know how to do. So in particular, if I were to multiply a matrix by itself in order to compute the matrix square, right? So this would be the definition of A squared. So you're giving me a matrix A of size n by n, and suppose that your objective is to compute the product of the matrix by itself, which is can legitimately be called A squared. So how will we do it? The matrix will have entries ij, and in order to compute the entry A square ij, what will I do? I will take the row I, column j, and I will multiply elements 1 by 1. So how will it look? I will multiply the first element in row I by the first element in column j, right? I will add it to the second element in row I, multiplied by the second element in column j. Third element in column, and I will add it. Then I will take the third element in row I, third element in column j, and finally the nth element in row I and the nth element in column j. Right? So far, no surprises, right? I hope you are with me. Okay. So now, having seen that, let me ask you a question. the question is, I would like to find the shortest path of length 2 or up to 2 from any vertex I to any vertex j. So what can I do in order to figure that out? I'm at vertex I want to go to vertex j. I can either go directly, if there is an edge, or I can go through another vertex k, and from that vertex k go to j, right? But I'm not allowed to make a longer route. You follow me? So suppose that the only thing I want you to compute for now is the shortest path from I to j that makes a stop at most one other vertex, k. Okay, so let's write down the mindset of doing that. So what will I do? I will go from I perhaps to vertex 1, which is one of the k's I can stop. Then I will go from k to j, or from 1 to j, and I'm going to consider it for the shortest path. But I don't know if it will be in the shortest path. So I'm going to take the minimum between this and the possibility of going from I to vertex 2, from 2 to j, and again I apply a minimum. Then I go from I to 3, from 3 to j, and apply a minimum to all of this. So I basically do all these different things, and I take the minimum of all of them. So here you have all the intermediate vertices on the path from I to j where I can stop. And in particular, I'm going to include a stop at I itself, which means that this distance will be 0, and then go to, so it will include also the case where I go directly from I to j without. So all these k stops, n stops between I and j, and taking the over all of them, I find the minimum length of all the paths via another vertex, including itself. So basically by, yeah, I got here a note that the connect stable. I hope you heard me well. You didn't lose anything I said. So tell me if you did. I can repeat what I said. So now observe that by taking the minimum over all of that, I'm guaranteed to find the shortest path of length up to 2 from I to j, and you know, you may want to include explicitly aij in the computation because it's a direct edge, but I claim that it is included because you can make a stop at I or a stop at j, and then add ajj or aii, which will give you this meaning. Okay. So I hope that this point is clear. Now, what's the connection? So first, this looks quite similar. Right here, I take the elements AI1, A1j, and multiply them. What did I do here? Instead of multiplying, what did I do? I did addition. So instead of having the binary operation of multiplication, I replaced it by addition. What did I do to combine all these multiplications? What did I do here? I did plus or summation or addition, right? What did I do here? I applied another binary operation, which is minimum. So if you think about it, Here I do two binary operations, multiplication and addition. The multiplication in a pairwise fashion and then addition across. Here I do addition pairwise and minimum across. But when it comes to operations, if you imagine a situation where you control the arithmetic logic units and you tell them, instead of multiplication, do addition, instead of addition, do minimum. In both cases, we are talking about binary operations. So a computer that is dumb enough to only receive the instruction, do this binary operation or that binary operation, will not even notice the difference. It will be the same algorithm unless you use one of the extremely sophisticated matrix multiplication algorithms which are beyond scope for this class. So is it clear to everybody that in terms of an algorithm, the n-cube algorithm that you learned in high school for multiplying two matrices of size n by n gives you the shortest path of length at most 2 from I to j by basically computing a to the power of 2 of ij in the sense of these two binary operations, plus and minimum. Does this make sense? So by doing something which is a one-to-one match to multiplying a matrix by itself, I'm getting all the distances from I to j of length at most, I'm getting the shortest path of length at most 2 from any I to any j. Okay, this is your chance to raise your hands if it's not clear. Because I claim that by doing that, I'm done. Why is that so? Because the computation of a to the power of 2 of ij gave me the minimum length of all paths from I to j via up to another vertex, meaning up to length 2. If I now take a to the power of 2, this a to the power of 2, and I raise it to the power of n, what will I get? I claim that you can easily convince yourself that if I raise it to the power of 4, I will get all the shortest path that goes through at most 3 intermediate nodes, or all the shortest paths that have lengths up to 4. If I raise it to the power of 8, which I will do first, power of 4, I get the 8 to the power of 2 multiplied by itself, I get a to the power of 4. Then I take a to the power of 4, right, multiplied by itself, get a to the power of 8. So at that point in time, I get the shortest distance from any I to any j, whose length is at most 8. And I keep multiplying the matrix by itself, so after a logarithmic number of steps, because I keep raising the power of the matrix by a power of 2 in each iteration. So up to, after logarithmic number of steps, I compute a of n, which guarantees that I find all the shortest distances of up to n from I to j. And remember the discussion we had in the context of the single pair shortest path, that if you have a shortest path which got to be longer than n, what did it mean? If you need to go beyond n, it means that you don't have a shortest path because only a negative cycle can imply that. Okay, so a negative cycle cannot happen, and because then the problem is not defined. So So this is really the basic, the whole argument here. And what can you tell me about the complexity of this algorithm? Each iteration is n cubed. And since you raise the matrix to the power of n, you do it in logarithmic log base 2 of n iterations, the complexity will be the time for one iteration, which is n cubed times log n, the number of iterations. Does this make sense to everybody? Please ask questions. That's your chance to ask questions. I really am eager to hear questions here, to be sure that you understand what I just described. Do you miss anything? Do you want me to repeat? I mean, even a question, just repeat something. I'll be glad to do it. You try to speak, Gauguin, but I don't hear you because you are muted. Unmute yourself.
Professor, can you repeat the like why the minimum? I'm not quite sure about the last slide about
the former slide.
Yeah.
Okay. Here's the question.
So why to find the shortest path of the length less than 2 from I to j include the aij in minimum computation?
Okay, so imagine that I'm giving you a graph, okay? And imagine that the graph is given to you by a matrix, the edges. Now, let me ask you, how can you consider or account for all the possible paths of length up to 2 between any vertex I and any vertex j? How can you do it? So let's do it, right? Give me a vertex I, give me a vertex j. How can I get from I to j by a path of length at most 2? I can either go directly from I to j, or I can go through another vertex, right?
Yeah.
So what are the vertices I can go to? I can go through vertex 1, and what will be the path? It will be ai1 plus a1j, right? Because my intermediate vertex is 1. I do a stopover at 1. Or I could alternatively go through vertex 2, from I to 2, from 2 to j. Which one is better? I don't know, but whatever the value will be better, I'm going to take the minimum among them. Okay? Then I have a third possibility. I can go from I to 3, from 3 to j. Is it better? I don't know. I take the minimum. So I take all these n possibilities, and since I take the minimum, I will have the value of the best, of the shortest path of length at most 2 from I to j. Just took all the possibilities. Does it make sense?
Yeah.
Now, since I computed all of this, I can now ask myself the next question: how to compute the shortest distance of at most 4? So think about it. How will you compute the shortest distance from I to j of at most 4? I need, if I know the distance from I to a middle point, which is up to 2 away, and from that middle point to j, which is also at most 2 away, in order to account or to consider all the paths of lengths up to 4, I need to go to a middle point which is up to 2 away, and from that middle point up to 2 to the other guy. And that's exactly what I compute when I do a to the power of 2 square. That's it.
Ah, I see. Thank you.
Okay, good. Great that you asked. I'm glad that you asked, because it just, you know, you do the dumbest thing. You just ask, what does it mean? And you list it. That's all. Okay, good. Thank you for asking. So I hope that this already clarifies why what we want to compute is a to the power of n, which we are going to do it by repeated things, because it gives me longest and longest pass. And as I explained, the longest pass I need to consider is of length n, because the shortest path must be found from such a path, otherwise it's not defined. And the complexity will be n cubed times log n. Okay, so this is, if you will, the naive algorithm, which underlines the more efficient algorithm that we are going to consider next, which is the algorithm that actually appears in the textbook, which, as you will see, is a refinement, in a sense, of the algorithm that I just described, where the main complexity contribution of the refinement will be that we will chop off the log n quantity. So instead of doing it in n cubed log n, we'll do it in n cubed. Okay, so this algorithm is known by the name Floyd-Warshall. And it is just going to go basically through the same rationale of the matrix multiplication, but in a more efficient way to save some redundancy, some multiplications, some doing the same thing again and again. So what is the basic idea? The basic idea is, again, inductive. And the induction is captured by the following. So what is the input for iteration I? Iteration k, I'm sorry, for iteration k. We assume that for any two vertices I and j, okay, we already found the shortest path between them that goes through vertices 1 up to k minus 1. So the vertices are numbered for n. In the beginning, the base of the induction is we know to go directly from every I to every j because we are given the list of edges. So the base of the induction is in iteration I, we already figured out how to go from I to j through the empty set of intermediate stops, right? Because we only know to go directly. The inductive assumption is that after iteration k minus 1, we know the shortest path from any I to any j that goes through vertices 1 up to k minus 1 as intermediate nodes. So now what I need to convince you is that in iteration k, I can add to my intermediate stops vertex k. If I can do that, I basically pushed my knowledge from allowing me to make stops in iterations 1 up to k minus 1 to nodes 1 up to k. So what is the basic idea? The basic idea is that to do that, I need to compute all the distances from I to j, either directly, where I don't make a stop at k, or by going from I to K, which I may use here some of the vertices 1 up to K minus 1, which I already computed. And from K to J, again, possibly using some vertices between 1 and K minus 1, which I already computed. Because remember, I computed following iteration K minus 1, all the shortest paths that make a stop among these vertices, 1 up to K minus 1. So if I now consider also making a stop at K using the knowledge I acquired before I started iteration K, I am in a position to enter the possibility of making a stop at vertex K. And that's the whole algorithm. So the whole algorithm is based on increasing the set of intermediate stops one by one. That's the whole algorithm. And the point is that each iteration will take me n square operations. And since I'm going to enter as intermediate stops all the vertices 1 up to n, it will be n cubed. So that's the big picture of the algorithm. And this figure captures it adequately. So this was the high-level description of the algorithm. I'm going now to describe it in both by way of code. I feel free to jump to it simply because I already gave you a higher level description. So the idea will be n is the, it's an n by n matrix. So n is the size of the matrix. D superscript 0 is the original matrix. And now what I'm going to do, I'm going to have three loops, one within the other. Here, I'm going to advance the variable k, which will, as you know by now, will include the list of intermediate nodes from 1 to n. So in the beginning, k will before, when we start, k is 0. So the intermediate node is the empty set, then it's the node 1, then it's nodes 1 and 2. And when we are in some random iteration, arbitrary iteration k, it's the nodes 1 up to k are going to be produced as intermediate nodes. And then I go for every vertex I and every vertex j. This could have been done basically in parallel, not serial, that these two. What do I do? I do the computation of dij, the distance from I to j, through vertices 1 up to k, is going to be the minimum between the distance from I to j via vertices 1 up to k minus 1. The minimum, this is one candidate for the minimum. And the second candidate for the minimum is going from I via the first k minus 1 vertices, go to k as an intermediate vertex, and add to it, going from k to j, so the same set of 1 up to k minus 1 vertices, and take the minimum between the two, meaning I either stop at k or I don't stop at k, which is exactly what I described here, right? I either go directly or I stop at k, and then I need to add the path from I to j and from I to k and from k to j. So this is it. This is the whole algorithm. In this slide, what I ask you to do is just ignore this part because it appeared in the textbook as one paper. Just look at this figure right here. So this is my graph. So you have here vertices 1, 2, 3, 4, 5. Okay. So, I'm going to do some simple drilling here, but that's basically what we are going to do, I believe, from now till the end of this chapter. So this is something you should be able to also go and revisit yourself later, just to make sure that you understand what the algorithm does. Okay, so here we are only going to consider this input. So what will happen? In the beginning, this is my graph. So these are the superscript 0 is basically the description of the graph, nothing else. Okay? Meaning this is the adjacency matrix of the graph. So let's be sure that this is the adjacency matrix. Here, the diagonal is 0 because the diagonal is reaching from node I to itself, which is 0. Here, for example, this is, let's make sure that we understand how this represents the graph. So the fact that I have a 3 here means that I have an edge from 1 to 2 whose length is 3, right? That's what we would expect. So let's check it. From 1 to 2, I indeed have an edge, which is 3. And for example, look at what will be the value, what value you expect from 1 to 4. You expect infinity, right? Because there is no edge from 1 to 4. There is an edge from 4 to 1, which is 2. So let's confirm that. From 1 to 4, it is indeed infinity. From 4 to 1, it's 2. So you see that this is really the, okay. Now, what I want you also to observe is that we use here this second matrix called pi. So what is pi? Pi is telling me where do I enter the vertex on the other side last. Okay, so where am I coming from? So clearly in the very original matrix, whenever I had an infinity, I'll have a nil here. And I also have a nil when I had a 0, because it's really meaningless. The one thing I'm going to capture here, the reason for having a nil on the diagonal is because I'm still interested to find negative cycles. And this algorithm, if it will give me a negative number on the diagonal, it will mean that there is a negative cycle. Okay, so bear with me. So now what's going on here? Let's look at D1. So what happens in D1? In D1, where can I make a stop? I can make a stop at vertex 1, right? So let's see what has changed here. So you see here that from vertex 3 to, I'm sorry, from vertex 4 to vertex 2, here I had an infinity, here I have a 5, right? So from 2 to 4, the ability to stop at 1 allowed me to replace the infinity by 5. So from 4 to 2 via 1. Let's verify that. From 4 to 2 via 1, you see, I get this 5. See, from 4 to 2 via 1, instead of getting the infinity from 4 to 2, I now have a 5. Okay, and the same thing will happen later. If you look at it, you will see that every step here, I I improve the prior values to the extent that the stopover in here in node 2, in addition to 1, makes a difference. Here I include stop at node 3, here at stop 4, at node 4, and here at node 5. So that's what it is. So you can verify that this is what this gives you. And the pi will be computed accordingly here. So when it comes to correctness, we are going to assume that the graph does not include any negative cycles. So following iteration k, dik is the shortest distance of any path from I to j that goes through vertices 1 up to k. And why is that? It's because we prove it by induction. It's the induction that I actually saw in my first introduction of the algorithm. This is an algorithm where the induction is both the description of the algorithm and the correctness. It's one of the same. So this is why it's correct. It's the same induction that the usual, and the complexity is n cubed. Why? Because we have n iterations for the intermediate node, and then ij, because we do it for every ij. That's exactly, we went over it already. I mean, that's, you know, from here, absolutely trivial from here. N. So, you know, n internal loops. It's 3 internal loops, so it's n cubed. So that's it. We exactly finished chapter 20. Chapter 25. If you would like me to re-upload these slightly revised slides, the difference, let me tell you, the difference is in the first 2 slides where I make the connection with matrix multiplication, but in my mind, the reason that I'm not sure it's necessary is because once you understand, it's very difficult to understand it if you don't hear me walk you through it. And if you hear me walk through it, I'm not sure you even need it. So, but if you want, I'll be glad to upload it. Just send me an email, I'll be glad to do it. Next big chapter that we are going to cover starting Monday will be the chapter of NP completeness, which is a big chapter. I strongly encourage you to be present and ask me questions, because what I found is that this chapter of NP completeness is very counterintuitive to people who come from engineering training. It's a very different way, and in a way, it's not what engineers would like to do. Engineers are smart. You give them a problem to do algorithms, they will figure it out. NP completeness is a completely different animal. I'm going to explain it, which according to my experience has been a bit challenging to students of this class simply because of their engineering backgrounds. It's not what they're used to ask themselves. So it's a different way of thinking. So I would encourage all of you to be present in the next lecture on Monday. Any questions about today's material? Okay, so we'll see you Monday. Bye-bye.